Third, design objective criteria or performance metric of control system is the steady state error. And steady state error measures the difference between the input and the output of the control system. So we have a set point and we have the response of the system. The difference between the response of the system and the set point is represent the steady state error, and this actually in the interval of time goes to infinity. That means for t goes to infinity we are going to calculate or to find what is the steady state error of the control system. So when we say time goes to infinity, this represents the response of the control system. For example, they'll go for the back, then at the end go to the infinity. When times go to infinity, this is the time and this is the response or CT of our control system. So the difference between the set point that we have and the output value represent the steady state error of the control system. Usually, in order to find the steady state error, we have to apply input to the control system. Then based on the applied input, we are going to measure the output. So the difference between the input and output represent the response, or I mean the steady state response of the control system. We already mentioned for these three functions or waveforms that we use to test the control system. We mentioned for them in chapter 1. So we have we may use one of these three functions in addition to the sine wave actually to test the control system. And the first function we call it the step function, and the step function or UT actually, which equal to the value and the time value of the time, which equal to 1. It will give you 1 whatever is the value of the time. So start from the point of 0 until infinity, the value of this function will be equal to 1 if it's ut, and its Laplace inverse is 1 over s. So we already mentioned for this one in chapter 2. Actually, when we talk about the Laplace transform, we said the Laplace transform of yt, or I mean now ut will give you equal to 1 over s. Okay. Then the second function that we are going to use is the ramp function, and the ramp function here as a function which is like f of t or r of t will equal to t. Since it is the input, we are going to use the simple r, so it's r of t equal to t, and its Laplace transform will give you equal to 1 over s squared. Okay, so the third function that we are going to use to test the steady state error of control system, we call it parabola function. So the parabola function here in the time domain is equal to rt equal to 1 over 2 t square, or t square over 2, and the Laplace of this function will be 1 over s cubed. So when we apply this function actually on a control system, that means it will represent the value of the input function rs. Okay, we say transfer function gs equal to the output, which is cs, over the input, which is rs. Each rs will be replaced by one of these functions, either 1 over s, 1 over s square, or 1 over s cubic. So we call it the function which used to test the performance of the control system. As we can see here, the selection of the test function or of the test waveform, it depends on the type of application that we are going to use. Okay, so for example, the step input or the ut here, or 1 over s, will be used since this function it has constant position. Okay, so since it's constant position, it will be used for system position or for the system position, which is it has a fixed position with respect to stationary target. So for example here, the tracking satellite in a geostationary orbit. So if you have a satellite, so this satellite actually it's even this satellite is moving, but it its movement or its location will be measured with respect to a fixed place, which is the stationary base station on the ground. So in this case, it's better to use the step input function to test this system. Okay, the second function, which is ramp function or ramp input, this ramp function actually it has a constant velocity. Actually we already mentioned this in the table here. You can see the table. The first ramp function or your step function, it has constant position. The ramp function, it has constant velocity. The parabola function, it has constant acceleration. So based on this physical interpretation, it will be used with the suitable application. Okay. So the first one, step input, we said it used with the for positioning of the, for example, like the satellite, which is move in a tracking with respect to specific or stationary target. The second one is constant velocity, and in this case, this one will we are going to use the ramp input, and this system actually it has ability to linearly increase the input here. Okay, so for example, in order to track a satellite orbiting at a constant angular velocity, so we are going to use the ramp input. Okay, if you have a satellite which is moving at a constant angular velocity, so we are going to use the constant velocity function, which is ramp input. If you have a satellite which is it has a position which is with respect to stationary target on the stationary base station on the ground, so we are going to use the constant position. So if we have for example a system which has constant acceleration here, so we are going to use the parabola input function. So in this case our focus will be more on how the speed of this system is increased. I mean, not only, no, it's not a fixed speed, it is accelerated speed. Okay, so we have so it's useful to track accelerating target, in this case like the tracking muscles. Okay, so these three type of system as examples for the three type of the input function to test the control system. Okay, so the next here we are going to highlight again about the open loop and closed loop and unity feedback and non-unity feedback. Okay, in the when we talk about the rough table, when we study the stability of the system using rough table, we said if you want to use rough table, you must use the closed loop transfer function, not the open loop transfer function. For this case, actually, we are going to focus more on the both we are going to focus on the unity feedback system, and in case of the unity feedback system we are going to use this transfer function either for open loop or for closed loop in order to study the steady state error. It's not like the rough table we said if we want to study the stability we need to focus more on the closed loop, but here we can use the GS and we can use the TS as we will see later on. Okay, so here the unity feedback, that means the value of HS equal to 1. There is no transfer function here, no block. So the value here will equal to 1, so we call it unity feedback system. The non-unity feedback system, that means the feedback here from the output is go through one other transfer function, which is HS. For that, we call it non-unity feedback. So for unity, HS equal to 1. For non-unity, we call it HS equal not equal to 1. So HS, it can be a value. It can be 1 over S, 1 over S squared, it can be 1 over S plus 1, and so on. So it's a value. Okay. So depends on the type of the system, we are going to get different value for the error. So this is the error value here, which is the difference between the input and output. ES will equal to RS here plus minus the output, which is CS in the case of unity feedback. Okay, here ES will equal to RS minus CS times HS. What is the value here? At this point we have CS times HS. Okay, CS times HS at this value, because the CS is here, go through HS, so the output will be CS HS. Then ES will equal to RS minus CSSH. So this is the difference between the unity feedback and the non-unity feedback and their effect or impact on the value of the error, which is used to measure the steady state error later on. So for unity feedback here, this is the output as we already mentioned. We said ES equal to RS minus CS. For non-unity feedback, ES equal to RS minus HS times CS. We said we can find the steady state error by using the two type of transfer function, either the GS or TS. We may use GS, we may use TS. Both can. So in the case of using the closed loop transfer function or the TS here, we are going to use these equations actually. For example, here you have a closed loop transfer function with the value, it's actually unity. We are talking here about unity feedback. That means H is equal to 1. So in this case, if you have this system, so you have the transfer function which is GS. This is the value of GS, and you have, it is a unity feedback, so this one is positive negative, which is the summing junction, and we have here CS. Again, go back to the negative here, and we have the input is RS. Okay, so at this point we have ES. We said from the formula this is actually CS, so the value of the ES for the unity feedback, depending on the value of the GS and RS, will equal to RS minus CS. Why CS? Because CS HS equal to 1. So the CS is go here also the same. This is CS go here again to here. So this is positive, this is negative. So it will become plus RS minus CS. But the value of CS actually, CS is a relation between the, or CS represent the value, the output of our system. And when we say the value of output, that means it will consider the whole system. And this gives you the transfer function, which is TS actually. When we consider the feedback, so this all value or all system transfer function, we call it the closed loop transfer function. So the value of CS here will equal to RS times TS, okay, or the input times the output, because the closed loop transfer function TS equal to the output over the input. So now if I substitute for the value of CS in the first equation, if we say this is equation 1, this one is equation 2, then ES will equal to RS, which is the input function, minus CS, which equal to also RS times TS. Or if I take RS here as a common outside the bracket, so I have 1 minus TS. Okay, now this will be the function of the error function in S domain. That means we are talking about the Laplace value or the S operator here equal to RS 1 minus TS. In order to find the, the value of the error or steady state error, we call it ESS. In order to find the steady state error, the steady state error usually is the limit when the time goes to zero, goes to infinity for the value of error. So you have the error function, which is the Laplace inverse of ES. It is 80. We said last time, if we want to find the Laplace inverse, the capital letter becomes small, the S becomes T. So we don't know the value, but we are talking like just about the symbol here. So the error, the steady state error, the formula said equal to limit time goes to infinity. Why time goes to infinity? Because we said steady state error is about talking about the time goes to infinity, not about the initial condition here. This is initial condition, we have transient response. But if we want to focus on the steady state error, we need to find what is the difference between the input function, the output response at t goes to infinity. So this is the definition of steady state error. Okay, so now if I want to apply the Laplace inverse for this formula here, I will should give you the value of SS, okay, like the capital error. Okay, so the value of ESS here, need to find the Laplace inverse for this theorem and the limit theorem. So if you go back to the tables in chapter 2, which give you the relations and the Laplace transform and Laplace inverse transform for the different formula, either for the derivative, for integration, or for the limitation and so on. So you are going to find that the limit of t goes to infinity, error of t, or the error function of t, will give you the limit. The inverse Laplace for this one will give you limit s goes to 0 SES. So if you go back just to the table, you will find this is the relation, or this is the steady state error for the value here. If you want to find the Laplace inverse for this function, which is limit et when time goes to infinity, it will give you limit s goes to 0 for SES. Okay, so now if I want to find the error value, or the steady state error value here, will be limit s goes to 0 s times es. What is the value of es? It is here. So it will be s times rs 1 minus ts. This is how to derive the relation or the function of calculating the steady state error using the closed loop. You can see here we are using the closed loop transfer function, which is ts. We cannot see any gs here. This is the formula to find the steady state error using the closed loop transfer function. We have one example here to apply this formula. So actually this is the formula that we get, which is ESS equal to E infinity limit s goes to 0 for SRS 1 minus TS. RS represent the input function. It can be unit, step function, parabola function, or ramp function. TS represent the closed loop transfer function, and this depends on the system type. Okay, so you can see here in this example number 13, you can see how to calculate the steady state error from the TS, from the closed loop. Later on, we will learn how to find it from the open loop also. Okay, so from the closed loop, if you are given the closed loop transfer function, which is TS equal to 5 over s square plus 7s plus 10, this is the value of TS. It's the closed loop transfer function, and the input is a unit step. When we said the input is a unit step or a step function, so that means the input of, or the value of rs equal to 1 over s. If the input is ramp function, it will be 1 over s squared. If parabola function, it will be 1 over s cubed. Okay, so from the problem statement here, rs equal to 1 over s and ts is there. So now we need to substitute for the value of es in order to find the formula. Actually, the formula said the error, the steady state error, equal to limit s goes to 0 s es, correct? So es here need to be found, which will be based on the formula s goes to 0 s times rs 1 minus ts. So this will be the formula that we see in the previous example here. In the previous, this is the formula. Limit s goes to 0 SRS 1 minus TS. You just need to apply or substitute for the value of RS, the value of TS in this formula. So ES here will equal to what? This is the value of ES equal to S square plus 7S plus 5 over S times S square plus 7S plus 10. From where we got it, this is the formula. Just substitute here. RS equal to 1 over S. So it is 1 over S. This is the S for RS times 1 minus TS. So the TS is here. You just find 1 minus TS. 1. This one we got it from 1 minus 5 over S square plus 7S plus 10. You just solve this one. It will be like S square plus 7s plus 10. So it will be also here s square plus 7s plus 10 minus 5. Okay, so for that you have 10 minus 5, it gives you this 5, and s square 7s 10 is the same s square 7s, s square 7s, this s square 7s, and the denominator is still the same, s square 7s plus 10, it is the same. Okay, so this is the value of es. If I want to find the error, so I need to find limit for this function. Limit s goes to 0 for this function times s. Okay, based on our main formula, s times es. So we substitute for s. When we multiply this function by s, if I multiply this one times s, this s will go with that s. So I still have s squared 7s plus 5, s squared 7s plus 10. So if s equal to 0, so this becomes 0, this becomes 0, this becomes 0, that one becomes 0. I have 5 over 10 and 5 over 10 equal to half. So for that, the error here equal to half. Or the e at infinity actually here is represent the value of steady state error. Hopefully it's clear. So now we are going to highlight how we can use how to use the closed loop transfer function to find the steady state error. And in this slide, we are going to focus on how to use the open loop transfer function to find the steady state error. So in this part, we are going to use GS directly. No need to find TS first, then find the error. No, you can use the GS directly to find the error. Okay. So consider unity feedback system here. If you have a unity feedback system, that means you have GS and you have one here. This is RS, this is the unity feedback system. So ES will equal to RS minus CS, okay. Then CS over RS, which is what is the closed loop transfer function of the whole system here? It will be CS over RS will give you GS over 1 plus GS. This is the feedback or the closed loop transfer function in term of GS. Okay, no TS. This actually it is TS equal to GS over 1 plus GS. Now we are going to find the value of error in term of GS. So the error here equal to RS, I put it here RS minus CS. What is the value of CS from this equation? CS equal to RS. If I remove this, it will be like times RS. Okay, so CS will equal to RS times GS over 1 plus GS. Substitute here RS times GS 1 over GS. So this can be simplified. So the value of the error in terms of the open loop transfer function, ES will equal to RS, which is the input of our system, over 1 plus GS. You can see here, this is the value of the error from open loop. From the closed loop transfer function, we said ES. Okay, from the this is for the open loop transfer function actually, and for the closed loop transfer function, which is that ES. From the previous example, we said ES equal to the value of RS times 1 minus TS. But here ES equal to the value of RS over 1 plus GS. Okay, so this is the difference between the two values, but both they will give you the same answer. Either you use the TS or you use the GS. In both cases, you are going to get the same answer for the value of error function. Okay, now when you want to find the steady state error, you just substitute S plus 0 or S goes to 0. You are going to replace the value of ES with its value, which is RS over 1 plus GS, because the formula said E infinity will equal to limit T goes to 0 ET, this is in the time domain, or equal to limit S goes to 0 SES, this one in frequency domain or after apply Laplace transform. So S is there S. ES is the value of ES here, which is RS over 1 plus GS. Okay. So in order to find the value of the error for different input, actually we said we have different input. Which one is the first one is the step input. So it is 1 over S. Second is ramp input. The third is the parabola input. So in each time, the value of the input here will be changed based on the use function. So if the RS is changed, the value of the error will be changed, and we will have different change or different steady state error for different input. Usually, the transfer function here of any control system, it's it's like this. This is the form or the general form of our transfer function, correct? It consists from numerator and denominator. In the numerator we have zeros, so we have zeros, number either 1, 2, 3, 5, depends on how many zeros do we have. And in the denominator we have pools. So it's factorial of or multi factors of s plus 0. So you may have, for example, s plus z1 times s plus z2, any number of s here. This is the numerator. The denominator will be s plus p1, which is the pool number 1, s plus p2, any number of pools. So this is the general form of our transfer function. And we have, if we have s at 0 origin, okay, at 0 means the value of the pool is 0. The value of the pool here, if I have s plus 1, for example, in the numerator, in the denominator, I will say the value s equal to -1. If I said s plus 2, so the value of s will equal to -2. But if I said s only, that means the value of the pool equal to 0. So if you have pools here in the denominator of your transfer function, the power of the pool at the origin will decide your system type. Okay, so for example, if you have the transfer function with s, with with the denominator s plus 1, so this is the highest power of s in the denominator for the zeros or pool at origin is 1, so this system is type 1. If s square, so it is system type 2. If s cubic, so it is system type 3, and so on. So the power of the pool at the origin will decide the system type, and the system type actually will affect your error value. Later on we will see how the system type will give you different error values for your control system transfer function.